first permanent position.
Correct.
Okay. So our first speaker, I don't think she needs any introduction, is Andrea Severing, who's at Cologne and is also a frequent visitor of Dresden. And she's going to talk about atomic-like states in intermetallic uranium compounds using novel spectroscopies.
Okay, thank you very much for the introduction. And first of all, I would like to thank the organizers for giving me the opportunity to present our work, and of course the Heraeus Stiftung for financing this event here. Today, what I will present is a collaboration between the Max Planck and University of Cologne, where I'm here funded by the German funding agency. Instrumental to our work are the PhD students, Denise Christovam and Andrea Marino, who is unfortunately not here, and Martin Sunderman, who is postdoc in our group. I will talk today more generally why we are interested in these intermetallic uranium compounds and why we think it is necessary really to have new techniques, new spectroscopies in place. I will explain this at the example of a model material, uranium gallium-2, and then later this afternoon, Denise will talk about a more topical material, uranium ditelluride. Okay, so F-electron physics, if you talk about uranium. These are the rare earth and the actinides at the bottom of the periodic tables. We are interested in mainly heavy fermion compounds. Heavy fermion compounds are intermetallic compounds, and you find a plethora of interesting properties. For example, unconventional superconductivity was first observed in heavy fermion materials, namely cerium copper to silicon 2, or uranium beryllium-13 that started the whole topic of unconventional superconductivity. They're called heavy. I do this really very, very quickly now for the younger people here, because the physics of these materials is driven by the hybridization of the F electrons with the conduction electrons. You may now envision that you sort of stuff all this entanglement, this hybridization into a large effective mass. So basically these fermions, entangled fermions, are behaving like heavy particles, and that's why they're called heavy fermions. I have here another diagram. It's called the Smetko-Smith diagram. These two guys developed that decades ago, where they sort of rearranged the periodic tables. We have here the 4F, 5F, and then the Ds, according to the localization of the magnetic moments. And we do find here cerium and uranium sort of at the border. Here we have magnetic order, here we have superconductivity. So they're here at the threshold between itinerant and more localized state. And that, of course, promises a plethora of interesting properties. We are now, more recently, looking at uranium compounds, and that is because all these hybridization effects are more extreme in uranium in comparison to cerium or the rare earth. That you can understand if you look at here. This is the atomic radius of a uranium 3+ and a neodymium 3+. So they have the same number of F electrons, but one is a 4F, one is a 5F. And you see that the 5F shell is clearly more extended than the 4F. So all these hybridization effects are much, much stronger in the 4F, in the 5F materials. And this, of course, is the reason why there is a lot of discussion going on. Should we now start from an itinerant picture? Should we think in terms of atomic-like states? I mean, for the rare earth, it's pretty clear we talk about atomic-like states, but for the uraniums, it's not so clear. And there has been, that already was put forward in the 1970s by Hill, simply a rule of thumb. Well, if the uranium and uranium are more apart, further apart than 2 times the atomic radius, they are probably more localized. However, if they start to overlap, they will be more itinerant. And there is an example. This is here, transition temperature versus uranium-uranium distance for this series, uranium transition metal germanium. By replacing the transition metal, you decrease the uranium-uranium distance and you suppress the ordering temperature. Here's antiferromagnetic order. Here's the Hill limit, this 3.5 angstroms, and you go into a Pauli paramagnetic state. So it's a nice rule of thumb, the so-called Hill limit, 3.5 angstroms. But this still doesn't tell us now how we should describe these materials. And should we use band structure or a multiplet approach? And I have chosen here two examples. They are isostructural, uranium beryllium 2 and uranium gallium 2. UB2, it's hexagonal, and you have here the tiny beryllium atoms, and therefore the uraniums, the distance is very small. They can be very close together. So this is really well below the Hill limit of 3.5 angstroms. And it's a Pauli paramagnet without any magnetic order. And here is uranium gallium 3. We replaced the small boron by the larger gallium. The uraniums have to move further apart, and we are well above the Hill limit. And it's a ferromagnet with a very high ordering temperature and a large magnetic moment. I'm showing here, this is the specific heat. You have the jump here where it goes into the magnetically ordered phase. And these heavy fermion materials, well, they're sort of in between. That's why we have these unconventional superconductors, the hidden order compound which you heard about this morning, uranium to silicon 2, these ferromagnetic superconductors, also this uranium ditelluride that Denise will talk about later this afternoon. But let's stick to our examples. I mean, UB2 is well described by band structure. That works, so that we don't need to discuss. But uranium gallium 2, although well above the Hill limit, is matter of a debate. I mean, you have papers in terms of band structures, other more local approaches. So we thought, well, that is maybe a good model candidate, that we are searching for signs of local physics in this material, which is well above the Hill limit. And that's what we're going to do. So if you look for signs of local physics, that means we talk about Hund states. We look for configurations. So we want to know if there is local physics, which configuration is the dominant one, determines our ground state. Does it come, I mean, in the intermetallics here, we always talk about F2, F3. We don't have other dominant ones. So is it uranium 4+ or 3+? And if it's one of the two, then we want to know what is the ground state symmetry, if you like, the crystal field ground state symmetry. I have to make a disclaimer here. If I say these two configurations, I talk about the one dominating and the one determining the ground state symmetry. I'm not talking about a really localized F2 or F3. There will be strongly hybridized two states. Actually, in uranium, you have even more configuration contributing, but these are the main ones. What we want to know, our ground state, is the F2 or is the F3 dominating? Or, and this was put forward by Gertrude some years ago, should we talk in terms of dual nature? Let's say we have a valence, a filling of the F of 2.4. That means we have 2 F electrons in F2, and the rest, fraction of a third electron, doing some other weird science or physics. And we start with uranium gallium 2 as a model compound. So here are I'm flashing here the multiplets. If you say, well, do we live in this Hilbert space, F2 dominating our ground state? Do we live in terms of F3? Please look here at the energy scale. Here at about 1 eV, we already would expect lots of multiplet states. The same actually for the F3 configuration. And then, of course, we have here our Hund's rule ground states in these two configurations, and they're further split by the crystal field. Now, if you put our uranium atom into a crystalline environment, we're splitting up the Hund's rule degeneracy. And there you also understand why it is so important that we do know what is the symmetry. Are we in this Hilbert space or in this Hilbert space? Here, we have a J = 4. So this is would be a non-Kramers ion. And then if you go into a hexagonal crystal field, we may have singlets or doublets. Whereas this here, we have a J = 9.5, so we have a Kramers ion, and we would for sure have a Kramers doublet as a ground state, which is very important if you want to model these materials. So how we get access to this? Well, the first thing, what you usually do is macroscopic measurements, right? You look at the static susceptibility. This I'm showing here the inverse of the static susceptibility of uranium gallium 2 versus temperature. And it's modeled here once with an F2 and once with an F3 crystal field type of scheme. They both describe the inverse of the susceptibility more or less, and the reason is that the effective moments of the F2 and the F3 are very, very similar. So you're not learning much here from your susceptibility. And the same, for example, if you look at the specific heat. Here we have the entropy of an Ln9 or Ln10 is very similar. So that you're not learning much from macroscopic data in the case of uranium intermetallics. You can think in terms of neutron scattering. I mean, I flashed before to you the splitting of the Hund's-rule ground state. I said it's of the order of 50 millivolt. This is a typical problem for inelastic neutron scattering, because all the cross-sections are really well understood in neutron scattering. You simply describe your spectrum and you know where you are. But unfortunately, intermetallic uraniums usually do not show any excitations. There are very, very few exceptions, but usually it's flat. There is nothing to be seen in the spectra. And I think this is one of the reasons why over the last years, people went more and more into these itinerant pictures using band structure, for example, for uranium ruthenium to silicon 2. And then there's, of course, X-ray spectroscopy. There we have a plethora of different methods. And I will slowly but quickly walk you through it. There is, first of all, the electron removal. We have photoelectron spectroscopy. We can do the core level. We kick out an electron. I put the X-ray absorption at the L edge in the same type because you excite from a 2p to a 6d. 6d is far out, so it is like an electron removal. These type of spectroscopies are sensitive to covalence, but they're really tough to model quantitatively. I'll show you here the core level, photoemission core level of UB2 and uranium gallium-2. This is data from Fujimori. They're published here. Gallium-2, yes, it looks different. There is a huge satellite here. This is the main emission line. That's the satellite. Here you have a main emission line, and you only have a tiny satellite. There's a qualitative difference, but it's hard to tell what does it tell you? You don't know. Well, then you can do X-ray absorption. That's what you do with the transition metals. Usually the position of the white line tells you what configuration you have. However, if something is covalent, you're not learning much because X-ray absorption is not sensitive to covalence. Now this is an X-ray absorption now into an F state. We're probing now the 5F. Then there are people doing branching ratios. In Grenoble, they do that. They like doing that. In principle, branching ratios should work, but the problem is, I think it's an accuracy problem. That is, the branching ratios of the M5 and M4 edge are very, very similar. The same actually holds for the N edge. Then you have to subtract the background. You do have to have an absorption correction. So basically that eats up the difference you have. And now you want to say, well, I have 2.4, I have 2.6 F electrons, and the F3 or the F2 now determines my ground state. I think that is a tough business to do. No, I have a problem with believing these data. And then there is the O edge also probing the 5F, but it's too much. The continuum, everything is very broad. So as a good or not so good friend of ours put it at one conference, spectroscopy made a mess. That we have in uranium ruthenium to silicon 2, it's just starting again with uranium ditelluride. And that's why we thought we have to do something else. We have to look into new spectroscopies. This is resonant inelastic X-ray scattering and non-resonant inelastic X-ray scattering. That's what you heard about already by how, although a different application. And what it will tell us is if we do RIGs, I mean, this is a bit like neutron scattering. You really look at inelastic excitations. We should see the multiplet structure and then know where we are. And NICS is a bit like an X-ray absorption, but I will show you why it is more applicable here and why we will learn something here. Like the linear dichroism in X-ray absorption, here the directional dependence of NICS will give us access to the orbital anisotropy and with that to the ground state symmetry. Here's some literature I'm flashing because I thought it's school, so I'm giving here, this is a book by Schulker. And also this is a nice article about resonant, but you also find the non-resonant part in this, and on also Mauritz, this paper has been important for us. So let's start with RIGs. We want to probe the 5F, and RIGs is a two-step process. We start with an X-ray absorption process. It has to go into the 5F, so that we are probing here. That's what we want to know. And then there is a second step, that's a decay process, and we want to know about FF excitations. That means we have to decay near the ground state. That's why I said, look at the energies. The multiplets are at about 1 eV. The X-ray absorption process, no matter what edge you look at, is several hundred eV or if not keV. Yeah, so we really do look at the decay near ground state to look at our multiplet excitations. That looks like that. We have an initial state. We do an absorption from a D10. The electron goes to the F. We always have a choice whether we look at the D5 half or 3 half because there's spin orbit split these D states. And then we look at the decay. And is the energy loss gives then, or this spectrum we are looking here is we can have elastic if you don't have energy loss. Or we can look at excitations that can be magnons if you are in a magnetically ordered state, phonons. We can have crystal field excitations. It's a bit like a neutron scattering spectrum, only that we have a much larger energy range. I mean, neutron scattering is usually limited to about 100 millivolt, has of course the great advantage of fantastic resolution. We are not that good with RICS, that's clear. But we have learned, for example, at the example of cerium compounds, I mean, there are only a few cerium compounds with very large crystal field splittings for the range of RICS, that we have huge cross-sections in RICS, where, for example, in neutron scattering, you only see a little tiny excitations, you have a huge signal in RICS. And that's what told us, okay, maybe we don't see any signal in neutron scattering, but we may have a chance with RICS. Now, of course, you have to decide which edge do I choose. I can have the 5D to 5F. That's the uranium 4045 edge. It's in the ultraviolet. You can have very good resolution. There is work on the oxides from Buturin, but they all show, yes, you have fantastic resolution, but a huge tail that dominates the signal. So that even if the excitation is at 1 eV, it's only a tiny, tiny hump, if you like, on this huge tail, despite the good resolution. So that is certainly then for intermetallics, I think, is problematic. Then there is the N edge. These are all these beam lines set up for the cuprates. And very successful experiments being done here. And this N45, which is the 4D to 5F, is in this energy range. Same good resolution as for the cuprates, about 30 millivolt. But unfortunately for uranium, this N edge is a very weak absorption edge. We tried it. And in the intermetallics, we have no signal. It was really frustrating. We went to 2 different beam lines because it thought this is a beam line, 2 different materials. It didn't work. There was nothing. And we still didn't give it up. We thought, well, there is the M edge. And the M edge for uranium is a very strong edge, very strong absorption edge. That is the 3D to 5F. And that is at a 3.5 to 3,700 EV. This is the tender X-ray regime. So we have a lot of intensity. But the drawback is the resolution, pushing the resolution here. You can have with X-ray good resolution when you're soft X-rays or when you're with hard X-rays. Soft X-rays, you do it with gratings. Hard X-rays, you do it with analyzer crystals, silicon or germanium crystals. However, for this X-ray energy range, we simply don't have the analyzer crystals. We don't have the materials. And these are now newer developments with quartz, but it's technically not easy. It's difficult. And there is now this one beamline in the world. This is the Max Planck high resolution tender RICS end station at DESY in Hamburg. It's been done up, upgraded here by the Keimer group from Stuttgart. It's been optimized for the ruthenium L3 edge, but we are benefiting here because the uranium M5 edge is in the same energy range. And there we can actually reach at the M5 edge an energy resolution of 150 millivolt. These are the data I will show you today. In this first experiment, we could not reach the M4. Later, we could reach it with 200 millivolt, and Denise will even show you data with 70 and 150 millivolts. So it is really improving a lot. This is thanks to these new diced analyzers, and they are made here by this guy, I might cite, he's from APS in Argonne. Another advantage, despite this resolution problem of the image, is, of course, 3.5 keV. We do not need to cleave. Unless our sample is air sensitive, we do not take any precautions. We can simply stick in the sample. So that is very nice when you work with uranium, because usually people do not like you cleaving uranium in their beamlines. And this is what we measured. This is now the example uranium gallium-3. It's part of Andrea's PhD thesis. Here is how we aligned the sample. We had the hexagonal C direction is sort of is the surface. And we, at the detector, the analyzer at 90 degrees, so if you measure specular, that is here this phi, 45 degrees, we do have the C direction along the momentum transfer. And that's the spectrum. We have here energy versus intensity. This incident energy here we used at the M5 edge. We have elastic, then we have this huge scattering here, and we have the spikes on top. And these spikes to us look like multiplets, whereas this here is charge transfer. I show you now in comparison UB2, I said that's the material well below the Hehn limit, and we still see this charge transfer, but all these spikes here, these multiplets are gone. So that tells us in uranium gallium-2, this more localized material, we really do see multiplets. Andrea now zoomed into this energy range, and that I show you here. This is from 0.5 to -2. Energy transfer, and now for two different incident energies. I think I forgot to say that when I showed you in the beginning the principle of Riggs. We can also, of course, at one absorption edge, always play a little bit with the incident energy, which is important because you reach different quantum numbers and then you can play with cross sections and you may enhance one or the other transition. We usually do a scan and we're only showing a few energies now here. So I show you here now these two incident energies. You can see, well, that's elastic, this is higher than that here, so we actually do see this difference in cross sections. And this is simply normalized to this most strongest excitation. What this means now, we can only learn from a model calculation, and that means we have to do a full multiplet simulation. That's what Andrea did. He is using this code. It's an open access code that was written by Mauro Zaberkort. It starts from atomic parameters that come here from this code, Cohen code. I think that's also open access. But now we are in a solid. That means we cannot really live with the purely atomic parameters. And that's been taken care of by introducing reduction factors. This is here the Coulomb 5F, 5F, 3D, 5F, the core hole 5F, and the spin orbit are reduced to these values, to 55, 60%, or to 90%. And that here is a simulation assuming we have an F2 ground state. Andrea is taking along some crystal field splittings. These were the splittings that were applied to the inverse of the susceptibility. There were these two models, for an F2 and for an F3, and that he takes along here. And I think it is a nice agreement. I mean, also here the simulations are, of course, normalized to this peak, and we think that fits very nicely. He did the same type of simulation for an F3, and no matter how much he tweaks now these parameters, there is no way that he can find a better agreement. That's the best he can get, so that from this tweaking of parameters in comparison, we state, well, we live in this F2 Hilbert space. It is the F2 that determines our Honsruhe ground state. I should say here that later that Denise will show that. We didn't have the data here, and I did not want to show it because Denise will show it. We could reach the M4 edge. And the other nice thing is that this strongest here excitation at 1 eV is suppressed at the M4 edge in case of F2, whereas it would survive if you have an F3. And that is something Denise will use. So, and that is really a smoking gun experiment where you clearly can say, well, if that excitation is gone, if you measure at the M4 edge, you know you live in an F2 space. But here we learned it's simply for modeling. And I think it's rather nice how Andrea could do this. So we live in an F2 Hilbert space, and now that means we can cancel this. We live here. And now our question is, so what is now the symmetry of this ground state? So we have to think, we now have to clarify the crystal field splitting. It does not mean we have to learn about the excited states. We only want to know the symmetry of the ground state. Because one thing is clear, with 150 millivolt resolution, we cannot resolve the crystal field splittings. That's beyond the capability of this experiment. But what we could try, and I've written out here the crystal field states, the JZ representations, and these are the corresponding charge densities. And you see they're very anisotropic. So you can imagine now, if I start having my momentum transfer along C, and I'm not moving away from C towards AB plane, I should see in my scattering some directional dependence, and that should be related to my charge density. And that's what Andrea did. So we have an initial state, one of these anisotropic ones, we have to assume. We do our experiment and for different incident energies, and now we start to rotate our crystal. And here are the data for the orange and the green incident energy. And this is 45 degrees. We are turning the crystal to 80 degrees. We're turning to 20 degrees. And you see here it is changing a lot, here less or so. Again, that needs some modeling. We have to apply the full multiplet calculation. And this time taking into account the different orientations of the sample with respect to the spectrometer for these six crystal field excitations. You see this here, orange for this incident energy is green for the 6 states. And I think it's pretty clear that one resembles this one rather well. This 2 could fit, this could fit, that clearly not, blue high, maybe that not. So from this we take, well, we either have a gamma 1 or a gamma 6, possibly a gamma 5. We cannot learn more from Rix, but we thought it's a lot. We didn't even expect to learn anything about the crystal field, but I think we got a nice approach here. So therefore, we went to NIX. That's what Hao already presented, because NIX is a bit like directional dependent NIX experiment is a little bit like the linear dichroism in X-ray absorption. So it's really made to probe the orbital occupation. NIX, non-resonant inelastic X-ray scattering. I quickly go through the introduction because you have partially seen it. It's a photon in, photon out experiment. We are scattering here at our sample, coming in with a wave vector, Ki, energy, and polarization. We have here the final state of our photons, and we're scattering at the electron cloud. You have an energy transfer and a momentum transfer. The momentum transfer is given, I would say, square root of the energy and the scattering angle. We are using this energy. We're coming in actually with very high energies for core-hole excitation. The energy, this excitation costs us maybe 100 EV, but we come in with 10 EV, keV, so far away from resonant. That's why it's called non-resonant for this excitation. And the nice thing is, being non-resonant, really, it's much easier to be quantitative in the modeling. We are truly bulk sensitive. We really don't need, I mean, the very first experiment years ago on a cerium sample, we even did with some ice around the sample. It's really amazing how bulk sensitive we are here. The downside is, of course, it's non-resonant, it's low count. So we really have to count quite a while. And what is important for us is having this high incident energies. I mean, looking at this, going to backscattering geometry, we can reach this large momentum transfers. And they're important to reach this so-called beyond dipole transitions. Beyond dipole is important because if we stay dipole, we know all the edges for uranium are just blurry and broad, and this beyond dipole is helping us here. This is what you have seen before. This is the dynamical structure factor. We have energy conservation, initial state, final state. We have the transition operator. You expand it here. And if you have large momentum transfers, you cannot truncate it. You have to take higher multiples along. That's why we have multiple contributions if you work with large momentum transfers. It's cleverer to write it this way, here in spherical harmonics, and to factorize it into radial and angular dependent part. We have quantum mechanics, this triangular and parity rule in place, meaning we do not have an infinite number of multipoles. That's what Hao pointed out. That's what he has in place here for this SNIX. Well, we are doing here either cerium, samarium, or uranium. You look at D to F, and then we only have this K equal 1, 3, and 5. And that looks like that. The radial part versus momentum transfer is showing here, and the dipole is, of course, very strong at small momentum transfers. It decays off. Then we get the octopole, the triaconta dipole. There are where we actually realize an experiment. So we are maybe have multiple excitations. And this is here now the angular dependent part. We've set this here to 1 versus energy transfer. We have here the dipole at higher energy transfers, and new excitations are coming up when we have multiple scattering. And that is important. It's also important that it is below the dipole, because that is what we're seeing here. This is a real experiment from Roberto Ciacciuffo on a polycrystal of uranium dioxide. If you do it at low, if you're dipole, it's almost like X-ray absorption. It's very broad. That is, of course, not captured here in the simulation because these states are very close to the continuum. So in reality, they're very broad. But if you go to higher multiplos, you go below, further away from the continuum, they're all of a sudden very excitonic. And that is very important for uranium. So multiple scattering at large momentum transfers, we have multiple scattering. It's more excitonic. If you now do such an experiment on a single crystal, so we look at the directional dependence as we would do in the linear dichroism experiment in X-ray absorption, we do see, yeah, I call it a dichroism, and that we can use for the orbital occupation. The bulk sensitivity, etc., the modeling I have already been mentioning. Of course, modeling, we again have to apply reduction factors. We have applied it already to uranium. We did uranium ruthenium to silicon 2, and we could determine the orbital occupation of uranium ruthenium to silicon 2. We found that it is a singlet, either a gamma 1 or gamma 2, very much on the JZ ±4 side. We can also look at cubic materials, and there I should say this UO2 and serum hexaboride. You may say, how boring, because the ground states are known, but for us it was important to do because Nix found the correct answer. So we can trust our experiment and our analysis. So here we can do cubic materials. We can look at the orientation of an orbital in the AB plane, for example, of tetragonal materials, things you cannot do with X-ray absorption in a dipole technique. And orbital imaging is something Howe spoke about. So we go to this beamline. This was now upgraded here by Howe's group. It's the same beamline, I should say, but a different end station than the RIGS, also in Hamburg. We come in here, we have here our sample, we're scattering here into the box where we have 12 analyzers and then into a surface sensitive detector. We do need resolution. We usually work with 700 millivolt resolution, which is sufficient to get something out. And that is our experiment, uranium gallium 3 again, intensity versus energy transfer. We have here elastic. Then we have the huge Compton, and on top of that, we have our excitations. Here the uranium 045 edge is what we are interested in because we are probing the 5F. No, it's a D to F transition. We measure this with much better statistics. That's what you saw before. We have this huge directional dependence. To understand what it is, we need to model. Andrea now wanted to check first, are we really in an F2? I mean, we know this from RIGS, but he nevertheless checked it. So he constructed from this an isotropic spectrum. He did an isotropic F2 simulation here to get his correct reduction factors. We're also playing a little bit in our simulation with the Q vector, which, if you want to know, I can tell you why we are doing this. So he can reproduce the isotropic spectrum rather nicely. He tried again to do it with an F3, but he could not make it work no matter how he was tweaking reduction factors. So clearly F2 is correct. And then he did it switching on a crystal field. So he's been playing with parameters that you all had different ground states at the bottom. And he did this now here for the 6 crystal field states. I think it's clear the gamma 1 still fits, the gamma 6 still fits, but here we can rule out the gamma 5. So we have these 2 states as a result. And with this, I'm already coming to an end. Actually, I would like to sum up. I think I could show you that tender RIGS at the uranium M edge not only has a strong signal, but we do see atomic multiplet structure in these intervalence band excitations of uranium gallium 3 in an intermetallic uranium compound. Also in Nix, we are seeing states that are very atomic. We learn from this, atomic physics is clearly to be considered in these materials. It's not just bands. I mean, sure, itineracy is there, but atomic physics is still there as well. We are learning which configuration is actually important to learn about our ground state symmetry. We can determine the ground state symmetry. I've shown this here, uranium, gallium 2, and now, of course, we have to see, well, we learned it's a gamma 1 or a gamma 6. What does this mean now for the material? Because we recall, it's a ferromagnet with a large moment in the AB plane. We do find a gamma 6 or a gamma 1, and how does this fit now the magnetism in this material? The gamma 1 is a singlet. It does not carry any moment. The gamma 6 is a doublet. It does carry a moment. However, if you have a gamma 6 ground state, you only can have a moment along C, not in the AB plane, and the moment would be smaller than 3 Bohr magnetrons. So that's not going to work. However, there has been work previously by Peter Thalmeier on various materials. Induced magnetism is the answer here. If the ratio of this intersite exchange and the splitting of a gamma 1 ground state, it has to be the singlet that is the ground state, and the gamma 6 not too far away, that actually will give rise to an induced moment up to 3 Bohr magneton. And this induced magnetism is something we are not only finding here, we actually also found this not in uranium, ruthenium to silicon 2 is the hidden order material, but we also looked at uranium nickel 2 silicon 2 or uranium palladium to silicon 2. These are antiferromagnets ordering at 150 K with substantial moments. And well, we find a singlet ground state, but there we can have a quasi-doublet, 2 singlet states, the gamma 1, the gamma 1 and the gamma 2, correct? And with induced magnetism, then we can explain the moment in these materials too. So I think this is something that is actually not so rare in these intermetallic uranium compounds. I mean, it's clear, if you have an F2 determining your quantum numbers, you may have singlet ground states. So we have published this here, and yeah, you can read this there. So, and with this, I would like to thank you for your attention.
Thank you for the talk. Very nice. Now it's open to questions. So.
You just simply speak.